first state and second state, right? Am I correct? Because this is a closed rigid tank. So there will be a time that the volume, okay, of the mixture, vapor mixture, will be equal somewhere along the way. At state 1 and state 2. Our state 1 is 10 degrees Celsius and our state 2 is 50 degrees Celsius. Okay, now in here, our organic liquid considered is refrigerant 1348. So usually refrigerant class composed of carbon and hydrogen. Usually the formula of this refrigerant 1348, because this is a general term, but there is a specific molecular formula for this, exactly the carbon to hydrogen bands. But in here, it's not specified because it is not our concern and focus to do the chemical reaction. Okay, so this is more on physical separation process. State changes or phase changes from liquid to vapor, a chemical reaction. That's why a general term, or shall we say, trade name known as refrigerant 1348. Okay, now since it is mentioned, we will never use the steam table. Instead, we will use the refrigerant 1348 table. It's the first thing, so that we can determine those quantities. Okay, what we need here is the volume of liquid, specific volume of the liquid, specific volume of the vapor, specific enthalpy. Shall we say also, do we need the internal energy here? Not so. Do we need the enthalpy here? Not so. So we'll focus on the volumes, specific volumes, right? So scratch paper, no scratch paper, empty black sheet of paper. Oh my God. So all you have to do is to be patient, to draw an illustration. It's mentioned here, the temperature versus the volume diagram. Class. My gosh. Oh my God. So y-axis. Oh my gosh. Sorry. Y-axis is our temperature. Normally the temperature and the pressure will be our y-axis. That's basically the format of the graphical representation of this type of problem. Oh gosh. Oh my God. So you write the given already, the data, so that we can also solve the problem. Let's solve simultaneously and compare our answers and solutions. Let's see if we obtain the same answer, though our solution is not the same. But the important is we have a valid a logical answer. It's gonna be like that because there are different methods how to solve the problem. But usually engineers would rather go to the shortcut method, usually to save time. But for the purpose of discussion, I'll be able to discuss this in detailed fashion. So that we know the basic theory and concepts, then we can formulate or we can adopt the most appropriate temperature. Okay, this is a temperature, y-axis. Okay, we have the volume on the x-axis. Okay, volume V. So this is a TV diagram. Okay. Actually, by theory and principle, we don't have to plot one by one, okay, because there are two states only. So, by concept, in this type of graphical representation, specifically the temperature and the volume, we will obtain a curve downward. So let's draw first the curve downward because it has been noted through series of experimentations from our previous scientists that during this relationship between temperature and volume, we can obtain a curve graph, and we don't have to prove that because it's already proven by our previous or old scientists before. Okay, so I have to draw now the graph. Then if you try to do this individually just to prove that you have to obtain a data sample of refrigerant 134A and you will go to the laboratory, okay, and do a series of tests so that we can really prove that our graph will be curved, okay, facing downward, okay. For example, if you want really to prove because you don't believe the theorem and postulate of our previous scientists, okay, then you have to go to the laboratory and get sample of this refrigerant 134A and heat that at 10 degrees Celsius and pardon heat also the to 50 degrees Celsius. Then you can plot your graph individually, okay, by having data, okay, for that. Locate the plot one by one. But in here, since this is already a proven theory, then we immediately draw the graph downward as it is really the concept in this particular problem. Or else it will lead you to how many days just to prove. Okay, so it will take you time. Okay, so all we have to do is to believe because this is really proven and tested through series of experimentations of our previous scientists in the past. Okay, now, so 10 degrees Celsius on this level here. So let's say I have here. So let's say this is a 100 degrees Celsius here, somewhere along here. Okay, let's say 50 degrees. Okay, like this. And we have 10 degrees Celsius here. Okay. Okay, we don't have to be exact because this is an illustration only, right? So 10 degrees Celsius, so we have to locate the volume. So this the volume will be on the horizontal axis, assuming that we already plot, and that's what we're trying to find out, right? Okay, this one. Let's see this one. You will draw an imaginary vertical line, okay, like this, okay, and connect that to the temperature 10 degrees Celsius. And we call this our Vf. Our Vf or our liquid volume, specific volume of liquid, okay? And then after that also, we have to put an imaginary horizontal axis line, okay, like that will touch to the curve, okay, like that. This will be your, okay, and this will be your Vg or vapor, okay, ganun. Okay, and this is at 10 degrees Celsius. Okay, and you have to put the point here. At VF class, this is known as saturated liquid. Okay, saturated refrigerant on 3,4-A liquid. Okay, and then at the VG, it will vaporize, it will become a saturated refrigerant 134A vapor. It's no longer a steam because we have another substance or component being considered here. Okay, now let's go to the 50 degrees Celsius. Okay, the same thing. You have to plot the temperature versus the volume. Okay, like this. Draw a horizontal axis and connect that here. Vertical axis like that, like that. Choo. Okay. We have now Vf again at 50 degrees Celsius. Okay. And now we need to project another horizontal line. Okay, and then here, project the vertical axis here. Okay, so that is VG. Okay, like that. Okay, so it's gonna be like that. Okay, as you can notice, the vertical imaginary line at 50 degrees Celsius will just be connected to the horizontal imaginary line at 10 degrees Celsius. Now this will be our V1, our 10 degrees Celsius, V1, okay? And then also our vertical imaginary line that connects to the VG will be our V2. Okay, like that. So you can say that I could say that the mass somewhere along the way at point 2 and point 1 are initial state at 10 degrees Celsius and 50 degrees Celsius final state will be assuming to be constant because this is a closed rigid tank, meaning this is not open. There will be no wastage. Okay, there will be no wastage of energy due to fraction losses or whatever losses like that, assumed to be exactly perfect. Okay, no recovery like that because the covering of the top is very closed. Okay, your x at 2. Okay, so x2 will be 100%. So the same as 1, or your x will be 1. Here, you get 50 degrees Celsius. X is close to 1 because 100% is just equal to 1. Okay, in a fractional form. Okay, this is your quality. In the problem, when it speaks about quality, that's automatically the dryness fraction. Okay, so in here we have the x1 and the x2 also. Dryness fraction in 2, so like this. Okay, and x1 also somewhere here. Okay, like that. X1 dryness fraction, x2 dryness fraction at 50 degrees. Yes, mass fraction. Or if you want it to be volume fraction also, it depends. Okay, what you want to solve. Okay, but here we are solving for mass of the vapor present. It's gonna be mg. Mg at 50 degrees Celsius. Okay, mg at 50 degrees Celsius or mg2 question mark like this means the vapor of the gas at point 2 at 50 degrees Celsius, and you have also to measure and to find out the mg1, meaning at 10 degrees Celsius. Okay, so since this is a rigid tank, our time like that. Okay, so it's gonna be the regular volume over the specific volume that we are trying to find out. Okay, so it could be the specific volume in 2 or it could be the specific volume in 1 because as I said, this is a closed rigid tank. As you can see also in the graph, V2 is equals to V1. And it's also equal to Vg. Look at the illustration. Okay, the volume, the specific volume of the vapor at 50 degrees Celsius will be equal to the volume at 10 degrees Celsius. V1, and of course also equal to V2. So we're very, very happy that there are three quantities are equal. It helps us to reduce our quantities to be solved by having this assumption. Okay, so we can have now Vg is equals to V1 is equals to V2. Ganon. Like that. So if this is the case, we can see total mass is equals to the total volume is 1.5 cubic. It could be Vg, V1, V2. Okay, this is our equation 1. Okay, equation 1 will be total mass. Total mass will be total mass 1 equal to total mass 2. Again, assumption, as I said from the very first part of this discussion, that the mass will be treated as constant. So total mass 1 is equal to total mass 2. At the same time, the specific volume of the vapor is equal to the V1 at 10 degrees Celsius and the V2 at 50 degrees Celsius. So those are specific volumes that we are trying to find out. Okay, good. So this is for equation 1. Okay. Now, what is the formula of Mg2 and Mg1 since we need to find out this one? Okay, so Mg2, okay, Mg2 by applying the Dryness Fraction formula, so we can say Mg2 is equal to the total mass into, right? Dryness Fraction 50 degrees Celsius is equals to Mg2 over the total mass 2. Okay? Or the total mass at 50 degrees Celsius. This is our equation number 2. Okay. We have to find out equation number 3 because we need to find a lot of quantities here. So x1 at 10 degrees Celsius, okay, is equal to Mg1. So vapor, mass of the vapor at 10 degrees Celsius over the total mass at 10 degrees Celsius. Okay, the total mass 1. Okay, like this. Zoom in. Okay. Okay. Now, since we have qualities here at equilibrium stage, and then this total mass is also 1.5 cubic meter over the specific volume of the gas or the vapor, V1, V2, we will solve this through our refrigerant 134A table. Okay, right? So we need to solve the Vg. Okay, how can we solve the V1 and V2? So we can solve this by applying algebra. This is the time that we use mathematics as an application, okay, in engineering course. Okay, because thermodynamics and physical chemistry are involving chemistry, physics, plus the application of mathematics. Okay, so this is algebra. Okay. Okay, guys, sorry for the disturbance. Okay, slope. Okay, take a look with a, with a graph. Let's take first at 10 degrees Celsius. It could be V1 slope in algebra. V1 minus Vf over, okay, I will put V1, okay, V1 minus Vf is equal to, okay, Vg minus Vf. Okay? This is at point 1 or at 10 degrees Celsius. Okay? Okay, guys? This one, huh? Ah. Okay? That's very clear. And then we have also equilibrium stage, liquid vapor mixture. So we have also equal to, look at the graph. So Vg, let's start with V2 first to make it parallel. V2 minus Vf. Okay. And then Vg minus Vf at 50 degrees Celsius. Okay. At 50 degrees Celsius. Okay, this is slope. Slope 1 is equals to slope 2 because of the reason this is in equilibrium stage in the liquid vapor mixture during saturation. Class, if we speak about saturation problems, there will be an equilibrium stage between the liquid and the vapor. Automatic. Okay? You don't have to worry. In most cases, it should be like this. In most cases. Okay? Now, our problem is so many quantities. There will be no problem because we have the refrigerant 1348 table. We can get the specific volumes there. Okay? Like that. Okay. Let's get now the 134A refrigerant table. But before that, our discussion will be on hold for a while. It will be continued after my regular exercise. Okay, see you later. I'll be doing the second part of my discussion after my exercise. Okay, so this will be hold for a while. See you later. God bless everybody. I'll come back later.